don't have to use this. This more right? Yes. Okay. You can use this. Go down. Can you reply? Yes. Okay.
Okay, start here. Good afternoon, everybody. I'm Rahman Purankar. I'm a postdoc here, and this is a work with colleagues in Finland on the energy management from a consumer perspective on the households. So let's start with the energy transition. Like this, if we can start.
Can you use go down?
Mm-hmm.
Yeah.
Okay.
This is go down. Yes. This is back.
I see. Yes. Okay, so energy transition is essential to mitigate the impact of climate change. We all know that we have to move away from the current fossil fuel-based energy generation toward more perhaps decentralized renewable energy dominated generation mix. And this entails a lot of pathways. Some of them involve end-use electrification, some energy infrastructure overhaul. We need to build sometimes in some locations a lot of transmission lines perhaps, or new generation capacities. Renewable energy is a big part of the energy transition, obviously, and people are talking about hydrogen infrastructure, energy efficiency, long duration batteries, and other emerging technologies, and DERs and microgrids. And our research overlaps with these four pathways for the energy transition. So we consider distributed energy system. DERs are generating and managing managing systems at the consumption point. And examples of the DERs are solar panels, electric vehicles, combined heat and power, and also storage systems and micro turbines and so on and so forth. They offer a lot of benefits. They improve grid reliability and resiliency by decentralizing basically the generation of the power. They lower the energy costs for households. Thus, they have implications for energy equity and climate justice. They reduce environmental impact of energy generation by providing clean decarbonized power. And also they reduce infrastructure and distribution costs. By adapting a lot of DERs in households in different neighborhoods, there is not that much need to build a lot of transmission lines perhaps or generation capacities. But of course, adopting DERs comes with different challenges. The basic one that is also the point of studies in recent years is the grid integration. The market and regulations are designed for decentralized dispatchable power currently. So adapting DERs is not easy. It needs an update in the regulation and policy. The other downside of DERs integration is the cost, the capital cost and maintenance cost for DERs for solar panels. We can think about the rooftop solar panels for that. Are expensive. Without the government incentive, there is not much benefit for low-income households to install, for example, solar panels. And also maintenance cost for these facilities is also expensive. Energy management is challenge for DERs. They require their own control systems to adjust and integrate with other parts of the household to get the most out of these DERs. They also impose some reliability and resilience challenges, and also some data privacy and security challenges as well. For example, if the system is infringed by cyber physical attack, the whole entire transmission line and in the grid may be exposed as well. So what we consider in this project is the home energy management system. So we think about home as an isolated entity smart home as an isolated entity, which has some interactions with outside world through the main grid. And there are different aspects when we think about the home energy management. There is HVAC systems. Obviously, we need to satisfy the electricity, heating, and cooling demand for the household or for the building facility. That is the main objective. And there are different aspects such as distributed generators, battery storage, main grid, EVs. We can think about this building as a prosumer. It sells and buys power from the main grid or to other households as well. There is energy market aspect, and we can think about as a microgrids by considering other homes. What we consider in this project are the highlighted boxes here. Okay. So home energy system management has been the focus of many studies in recent years. So different models look at this problem from different angles. From the parameter perspective, a lot of studies consider the deterministic parameters for the home energy management systems. They rely on forecasting or run multiple scenarios independently. Some of them consider uncertainty by modeling this management and control problem as stochastic programming, robust optimization, and so on and so forth. The objective mostly involves expenditure of some sort, variable cost, maintenance cost, levelized cost of generating the electricity, for example. Some environmental aspects is considered by the way of emission cost, economic incentives, such as maximizing the revenue of the prosumer is another aspect that is considered, and some studies consider battery degradation, outage, and load shedding. From a solution perspective, some studies rely on highly stylized model-based optimization models. So these are models that we already know how to solve. We usually define them in a solver, commercial solvers, or try to solve them as an optimization problem. So they have great advantages. They provide exact solution. They are explainable. And also they provide a lot of good analysis like the dual signals and dual variables as well. But they also come with downsides. For example, we need to make heavy assumptions on the data and constraints when you want to use these highly stylized optimization models. And they may not have great performance on out-of-sample scenarios. And also sometimes they can be intractable to solve as the problem size grows. There is another trend in recent years on the home energy management, which is which consider the model-free approaches, like reinforcement learning. So these models are scalable, are applicable to complex setting. We don't need to make heavy assumptions on the objective and constraints and problem types. And they sometimes, depending on the context, can provide good approximate solution. However, they don't provide any performance guarantee usually, and sometimes they are not stable in different settings. So what we consider in this project is the sector coupled households, buildings, where we couple the prosumer. We look at the building from a prosumer perspective, and we consider thermal demand, also cooling demand, as well as HVAC and transportation with the way of EVs. So different sectors of energy are coupled in our model. And we also adopt a deep learning, reinforcement learning, mixed integer programming for the resulting problem. So this overall framework gives us a control policy where we can control and adjust the energy management for households and buildings. The objective function, before introducing the model, I have to mention that this project is motivated by a technology company in Finland. So the objective function here from presumer perspective is to maximize the presumer revenue. And the constraints are subject to battery and heat storage constraints, HVAC, building temperature, and some other constraints in the problem. So most of these constraints can be modeled by some linear approximations. However, some of them, like HVAC system constraint, are highly nonlinear, non-convex constraints. So there are different solutions. Some studies used energy simulation tools like Energy Plus to approximate the outcome of the HVAC power and with regard to the temperature and comfort zone. Some others use the approximate equations, piecewise linear, and some other equations to approximate the non-convex equation. What we initially do, this project is still in the initial phases. So we started with the regression model to approximate the output of the HVAC. And surprisingly, it works well so far. We will see its performance in the actual setting as well. So this is the optimization problem we have. We have the object function, we have some constraints. Some of the constraints are highly nonlinear and non-convex. So we cannot solve this problem with the traditional commercial solver. We cannot define it to Groovy, let's say, and want it to solve. What we do is instead, we rely on the deep reinforcement learning mixed integer program. So reinforcement learning is defined by 5-tuple array. The first one is the states, where we define in this study as the hourly demand, solar radiation, state of the charge for storage facilities, indoor, outdoor temperature, and also price, which is given as real time and for overhead price here. Actions include battery charge and discharge. These are the actions that the controller has to make for every time period. HVAC power and the power trades with the main commit. So for reward, what we consider is the revenue minus the penalty for violating the temperature and balancing constraints. And also there is gamma is discount factor, and there is P here shown here because reinforcement learning is initially developed based on the Markov decision process, which assume a probability of transition. So in many cases, reinforcement learning cannot be solved by dynamic programming because either the space, state or action space is continuous or the solution space is too large. So what is proposed is to approximate what is called the action value function. Basically, this Q function is the estimate of the expected cumulative reward for action AT if action AT is taken at the state ST by following policy time. So without going to the details of the reinforcement learning and the Bellman equation, in deep reinforcement learning, we replace the approximation of this Q function, this reward function, with a deep neural network. And that has been done for several years now, and we also use the idea. So to come up with the solution approach, we adopted the solution approach from previous study for now. And basically, it consists of 2 phases. In the first phase, it is the training process for the deep reinforcement learning. It starts by defining the initial parameters for both deep neural network and reinforcement learning, and iterates through the episodes and epochs for the reinforcement learning. So after the end of this first phase, what we have is the parameters, weights, and biases for the neural network system, neural network design. In the second phase, we take these weight and biases and formulate a mixed integer program. And this has been done in recent years by not in the context of energy, in the context of operation research mostly, where basically we model the behavior of the neural network, the entire behavior of the neural network, with a mixed binary programming. And this allows us, combination of the first state and the second phase allows us to solve this nonlinear and non-convex problem approximately not exactly, because we cannot provide exact solution for non-convex. And so for the results, it is still in the initial phases. We don't have many results, but we have a few results that I'm going to show. We considered the technology company based in Finland. They provided the data for ambient temperature and comfort temperature, and all other data is obtained from the previous studies. So this shows the convergence of the algorithm, basically convergence of the reinforcement learning, the agent and how it learns what to behave in each time period. And as we can see here, the reward is non-decreasing, and it shows the agent actually learns after a few thousand of the episodes. This one shows the day-ahead power balance for an exemplar winter year. Basically, what we can obtain, the takeaway here is that the agent buys and charges in low price hour, and intuitively sales and discharges in high price hour. And for the first phase, our algorithm consists of two phases. We only get a feasible solution for the problem in the second phase. However, we observe that first phase alone also performs quite efficiently, as there is only a few of the violations, balancing constraint are violated throughout the day from the first phase solution. And of course, this violation is disappeared in the second phase of the solution approach. A few takeaways: machine learning can help solve high fidelity energy management problems that are otherwise intractable with traditional optimization techniques. Deep reinforcement learning has the potential to provide good approximate solution, but as we also see from this project, it requires tedious parameter tuning. For the next step, we want to include heat pumps, heat storage, flexible load for demand response. And the solution, the intent is to make the framework more generalizable for other buildings as well. We use the data for this company, technology company, but we want to generalize the approach for other companies as well. And application-wise, eventually we want to deploy this whole framework and test it in the actual setting of the company. And some references, and with that, I conclude my presentation. Thank you very much.
All right, we invite some questions if you have any. I'm curious what's, and I know from driving the violation is that sort of rewards to each given pricing period in a future system, or I'm just curious.
So
how you operate that.
We cannot directly impose like balancing constraint in the reinforcement learning framework. What we do is that we penalize the objective function, the reward function, by violating for the violation of the balancing. So that is what gives us some violation in some periods. However, the second phase fixes those violations. So at the end of the second phase, we don't have any violation of the balancing constraint for thermal balance constraint or electricity balancing constraint.
All right, thank you, sir.
Sure.
Double check.